We've been discussing relations and all of these properties, reflexive, irreflexive, symmetric, antisymmetric, and transitive, and I figured I would put them all on the board before we do an example or two. And you see these two are similar. This says for every single possible element in the set A, you must have that the x relates to itself, or the element x comma x is in the relation, and this for every single element in the set A, x comma x is not in the relation. And then the others are all implications. So, we will go through them more in an example, but the other three, symmetric, antisymmetric, and transitive, are implications, and then these three, reflexive, symmetric, and transitive, when we have a relation satisfying all three of those, this is an equivalence relation. So now for our first example, let's consider the relation R on, and this is, remember, the power set of the integers. So this set contains all subsets of the integers. And we say one set is related to another set, provided, A is a subset of B, okay? And we would like to figure out all these 5 properties, or which one of the 5 properties this relation satisfies. Well, first of all, reflexive would say for every subset, we need A to be a subset of A. Is this true? Yes. A is always a subset of A, which means that A relates to A, or A comma A is an element of the relation, and so we get yes, reflexive. Now, irreflexive is, as we've discussed, it's different than just not reflexive. It's still a for all. So for all subsets, we need it to be not related to itself. Well, it's not irreflexive, and to disprove it, you just need one. So you take one element in your set 2 to the z. This is a set containing 1, and this set is related to itself because 1 is a subset of itself. So it's not irreflexive. This is a counterexample. Irreflexive says that for all, in this case, subsets of the integers, you cannot be related to yourself. Okay, symmetric. This one's a little bit more interesting. So we need to start with, this says for all 2 to the z, if A is a subset, I'll phrase it this way, then we would need B as a subset of A. I've changed the related, this part, into what it means for our particular relation. Well, this is definitely not true, and here's a counterexample. So maybe I will erase this. This is the statement. If we had this true, then our relation would be symmetric. Okay, but a counterexample is coming. Let A be this set and B be this set. Okay, these are both elements of 2 to the z. Then we notice that A relates to B, because A is a subset of B. B does not relate to A because B is not a subset of A. So this says this is not symmetric. I will put that here. And here is a counterexample. Next we have antisymmetric is an implication. Okay, and it says that if A relates to B and B relates relates to A, then we must conclude that A equals B. And if we can, we have antisymmetric. So let's translate that for this relation. Then we have A is a subset of B and B is a subset of A. And this is equality of two sets by definition. So the answer here, which we've just argued, is yes, it's antisymmetric. Okay, now finally transitive. So this one, again, is an implication, but we say if A relates to B and B relates to C. Now we need to conclude that A relates to C. Remember I say this, the middle ones match. Then A would relate to C. And if we can conclude that, then we say the relation is transitive. But what we can say immediately from this is that A is a subset of B and B is a subset of C. Okay? Now, you might remember this from a homework. If A is a subset of B and B is a subset of C, then A is a subset of C. If you don't remember, we can prove it. In fact, it's good to always think about these proofs with sets. So if we let X be an A, then as A is a subset of B, we have X's in B. And then as B is a subset of C, X is in C. Okay, so therefore, we started with something in A, and we have shown it is in C. So therefore, A is a subset of C, which means A relates to C. And so this one is a yes. Okay, so this relation we have found, let's see which ones did it satisfy. Maybe I'll star them. This one was reflexive. No, no. It was antisymmetric, and it was transitive. It is not an equivalence relation because we're missing symmetric, but it is a relation satisfying these three properties. Now we take R to be a relation on a set. Okay, and we want to prove R is symmetric if and only if R equals R inverse, and this is the inverse relation. If you recall, we get R inverse by taking every pair in R and flipping it. Then you have an element in R inverse. Okay, so the nice thing about this example is it's an if and only if, and we get to practice showing two sets are equal and things like this. So if I call this first one P and Q, you know, when we prove an if and only if, there's two directions to prove. We have P implies Q, and then we have Q implies P. So first I will move in this direction. This is the P implies Q, and so I assume that R is symmetric. And I need to show R is R inverse. And this means, this is two sets, right? So we need to show one is a subset, so I need to show R is a subset of R inverse, and R inverse is a subset of R, right? This is how we show two sets are equal. Okay, well, we take an element in R. Well, typically we would say let X be an R, and I started to write it, and maybe I will to discuss it. You see, we know what the elements of R look like. They are ordered pairs. You know, a relation in its most general terms is just any subset of A cross A. That's a relation on a set A, okay? So instead of just taking some X, I know specifically I can write it as a, you know, a X comma Y in R, where X is in A and Y is also in A. So I take an element in R, okay? As R is symmetric, Well, the meaning of symmetric is if you have a pair like this, then you flip it, yx, it's also in the relation. We know, or we have, that yx is in R. Okay? Well, now, by the definition of the inverse relation, and that yx is in R, we have, you flip it, x, y is in R inverse, and this shows that R is contained in R inverse. So we have one direction, and now to show, maybe I'll even make this clear, this direction was subset, this was R subset of R inverse is here, and then we need R inverse subset of R will be here, okay? So here we just take a pair in R inverse, and then by the definition of R inverse, we know that if you flip it, yx is in R. Now R, our assumption is it is symmetric. So since R is symmetric, this means that xy is an element of R. And if you look what we have shown, we started with something in R inverse. Maybe I will just finish the same way, showing R inverse is contained in R. Okay, so we have these two directions, and in fact, these two complete this direction of the proof. Okay, now, very good. Well, the other direction of the proof, going this way, this is in blue. We assume R equals R inverse. And we want to show R is symmetric. And as we have discussed, showing something is symmetric, the property of symmetric is an implication. It's an if-then. It says if x comma y is in the relation, then y comma x is in the relation. Okay, so we just say, we assume we have xy in R. Okay, well, since R equals R inverse, we know xy is in R inverse because, well, the sets are equal. In particular, R would be a subset of R inverse. Xy and R would mean that it is in R inverse. And then, by the definition of the inverse relation, we have yx is in R, which shows R is symmetric. And this is exactly what we needed to complete the proof. Okay? I would like to prove a statement about equivalence relations, which once we understand what it's saying, it will not be too hard to actually prove. So you take an equivalence relation R and on a set A, and you want to prove that this set A equals the union, basically, of all the equivalence classes. Well, okay, so first of all, there's this notation which we may not have seen before. Let's talk about that for a moment, and then we will look at the example behind me. So if I look, let's say I do something that, I won't even use A. Let's say I do something that we are familiar with. Let's say I write B1 union B2 union B3. Okay, this consists of every possible element that is either in B1 or B2 or B3, and I don't need, parentheses at all, because if you put parentheses here or you put parentheses here, it'd be the exact same set. Okay, well, I could write this using this union, this big U notation, like this. It's a union. Let's say I in the set 1, 2, and 3. And often what goes down here, this set 1, 2, and 3 is called an index set when you're dealing with this notation. And then I could say B sub I. These two are saying the exact same thing. In this case, we only have 3 sets. This has 3 elements, and it says you take the union of B1 and B2 and B3 like this. But you could have, if your set A is infinite, as it is with the integers in this example, the index set that you put underneath a big U might be infinite, and that's okay. You would just, this notation stands for all possible elements that are in, at least one of these sets. So here, this notation, it says this is all possible elements that are in at least one of the classes. Okay, so now let us discuss this example, and we've seen one like this in class. If I take the integers and I take congruence modulo 4. So congruence modulo 4, to remind you, I will come back over here with my side work area. Congruence modulo 4 is as follows. We say x is congruent to y mod 4, provided 4 divides x minus y. Okay, so we showed in class that is an equivalence relation, and then the equivalence classes, so this set is everything that relates to 0, and you could check, 12 minus 0 is 12, 4 divides that. Or for instance, in this class, everything that relates to 1, minus 7 minus 1 is minus 8, and 4 divides that. Or, okay, maybe I'll jump down and do one here. This is the equivalence class of 3. Okay, we could take, 19 minus 3, 16, and 4 divides that. Okay, so these are the equivalence classes here. We also discussed, for example, this is equal to the class of 6. Okay, you see 6 here. 6 is certainly related to 2, but also we proved in class that for any equivalence relation, the classes are either identical, and that's when 2 representatives are related. So 6 and 2 are related under congruence modulo 4, or equivalence classes are disjoint. Okay, but now to what this theorem says, you can see, maybe I will get another color, you can see here, to see that you get all of the integers, you see here's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Minus 1, minus 2, minus 3, minus 4. You could fill out the whole integers with these classes. Okay, now let's prove the theorem. And this theorem is about 2 sets being equal. One is capital A, and one is the union of all equivalence classes under some equivalence relation. So I'm going to, as we do anytime we show 2 sets are equal, first we argue subset in one direction and then subset in the other direction. So I will take an element in A. I need to show that it is in this union. Okay, well, R is an equivalence relation, which means in particular R is reflexive, which means X relates to X, or another way to say that is that X is in the equivalence class of x. Now, this is something that we also proved in class, and I could have just quoted it. As shown in class, x is an x, but it didn't take very long to go over why it was true again. So x is in its own equivalence class. Therefore, x is certainly in the union of all of them because it's in one of them. It's in its own, okay? So it's definitely in the union of all of them, and that establishes the subset in this direction. So now we need to argue in this direction. Okay, so now we take an element in the union of all the equivalence classes, capital A, excuse me, the class of A. Well, if x is in the union of a bunch of sets, it means it's in at least one. So then there exists with x is in this class. Now the definition of this class is the collection or the elements. The definition of this is the elements in A that relate to little a. So in particular, if you are in this class, you're an element of A. So in particular, we see x must be in A. And this gives the subset in the other direction. And this completes our proof. So the proof really wasn't too bad. As I mentioned, it wouldn't be once we understood what this was saying.